Welcome to this visual explainer. Today, we are tackling a massive and honestly incredibly fascinating topic, electrostatic potential and capacitance. Now, I know usually this topic feels like hitting a heavy wall of complicated math and endless integrations, but hey, we're going to do things differently today. We are going to strip away all those messy equations and focus purely on the core visual concepts so we can truly understand what is actually happening behind the formulas. Let's make sense of the invisible forces all around us.
All right, let's dive right into our roadmap for today. First, we'll cover the foundation with work energy. Second, potential and energy. Third, equipotential surfaces. Fourth, dipoles and fields. And finally, number 5, conductors.
Section 1, the foundation, the rules of the universe. Okay, our starting point is the good old work energy theorem. You probably remember this. It tells us that any work done on a system changes its kinetic energy. But what if we do that work incredibly slowly? I mean, so slowly that we keep the velocity constant. In that case, the change in kinetic energy is exactly 0. So our active effort, the work we're putting in, has to go somewhere, right? It can't just vanish into thin air.
And here is the absolute crucial point. When we, acting as an external force, do work extremely slowly against a conservative force, like gravity or an electrostatic force, that work doesn't turn into motion. Instead, it stores perfectly within the system as potential energy. We do the work, and the system basically saves it up like a giant battery. This right here, this is the absolute foundation of everything we're about to discuss.
Moving on to Section 2, Electrostatic Potential and Energy, the journey of the test charge.
Instead of getting totally bogged down in the math, let's visualize this as a simple 3-step journey. First, imagine a tiny positive test charge starting infinitely far away, feeling absolutely zero effect from anything. Second, we start pushing it closer to a really powerful positive source charge. Since they're both positive, they naturally repel, meaning we have to physically force them together. And third, because we moved it super slowly, all of that mechanical work perfectly transforms into stored electrostatic potential energy, which we denote as U.
To really make this stick, I love this amazing analogy from the source material. Imagine the massive source charge is a powerful mob boss, and the tiny test charge is a smaller street thug who's been causing trouble in the boss's territory. Now, that thug isn't going to just walk up to the boss willingly. The boss's men have to drag the thug in completely against his will. The work done physically dragging them together creates this massive tension, or in our physics terms, massive potential energy. Now, if we take that total stored potential energy, the tension of that entire system, and we simply divide it by the value of the tiny test charge itself, we're left with the electrostatic potential. We represent this with a V and measure it in volts. Basically, potential energy is the total energy of the system, while potential is just the energy per unit of charge. Think of it as the electrical pressure at that specific spot in space, completely regardless of who you drag there.
Section 3, Equal Potential Surfaces, Navigating the Electric Landscape. Before we map all this out, let's stop and ask ourselves a quick question. What actually happens to potential energy when you bring an electron near another electron? Well, bringing two negative charges together causes extreme instability. They absolutely hate being near each other. Forcing them together causes a massive spike in potential energy. So to lower that energy, they naturally want to push apart to a much more stable state. To avoid that extreme instability, charges map out what we call equipotential surfaces, or EPS. You can think of these kind of like the contour lines on a topographic map. The rules here are incredibly elegant. The potential is identical everywhere on that specific surface. Because it doesn't change, it requires absolutely zero work to move a charge along it. They cross electric field lines at perfect 90-degree angles, and where the field is the strongest, these surfaces bunch incredibly close together. This brings us to a fascinating duality called the RDX trick. Check this out. If two charges physically attract each other, their equipotential surfaces visually repel and bend away from one another. But if the charges themselves repel, like two positive charges, their equipotential surfaces actually attract and squish together. It's such a brilliant visual shortcut to keep in your back pocket.
Next up, Section 4, Dipoles and Electric Fields, the dual nature of charges.
Because a dipole is perfectly symmetrical, one side is perfectly positive, the other side perfectly negative, it creates a really fascinating effect. If you measure the potential anywhere along the equatorial line, basically directly cutting through the middle, it will always be exactly 0. The positive push and the negative pull are totally identical at that exact distance, perfectly canceling each other out. But when we drop this dipole into an external electric field, we see another stark contrast. If the dipole aligns perfectly with the field at 0 degrees, it is in stable equilibrium. It's happy, it's peaceful, and the potential energy is at its absolute lowest. But if you force it to face exactly opposite the field at 180 degrees, that is unstable equilibrium. The potential energy is incredibly high here. If you nudge it even a fraction of a millimeter, it is going to aggressively snap back around. So you might be wondering, why the big focus on 90 degrees? Well, to measure these extreme states of equilibrium, we really need a baseline. We actually establish our zero potential energy reference point when the dipole is completely perpendicular to the electric field at exactly 90 degrees. That's our zero mark, and it allows us to calculate all the highs and lows from there. Finally, let's hit Section 5, Conductors and Charged Behavior, Grounding the Theory in Reality.
Whether we're talking about a conductor that's hollow like a shell or completely solid all the way through, charges absolutely hate being near each other. If you dump a bunch of electrons onto a solid metal sphere, they instantly repel each other and rush to the extreme outer boundaries of the surface. And because they all fled to the exterior, the inside of the conductor is left completely void of any net charge. With no charge inside, the internal electric field becomes a perfect zero.
And that brings us to a massive realization, one that trips up a lot of people. A zero electric field inside a conductor does not mean the potential is zero. Remember the relationship we talked about? The electric field is the rate of change of potential. So if the field is zero, it simply means the potential has stopped changing. The potential inside the conductor is just a flat, constant value. It's exactly the same everywhere inside as it is on the surface. So I want to leave you with this. Knowing what we know now about charges rushing to the outside, leaving that internal space with a peaceful, constant potential and zero electric field, how can that empty space inside a hollow conductor become the ultimate shield? Think about being safely inside a metal car during a massive lightning storm. That exact principle is what keeps you alive. Thank you so much for joining me on this explain.